My name is Tan Hao, and today I'll be briefly going through this concept of infinite dimensional linear algebra. Actually, initially I had wanted to study on this topic and uh, become quite acquainted with this topic of functional analysis. Is another word for infinite dimensional linear algebra. Uh, but in the end, I found out that functional analysis is actually much more involved than I expected, and I don't think I'll be able to understand functional analysis anytime soon. So, but since I already made this presentation halfway, I decided to present it anyway. So, let me just put it out there that I am definitely not an expert in infinite dimensional linear algebra. I haven't even took a course in it. So, what I'm sharing over here is I'm just sharing my enthusiasm about this subject instead of and so don't take anything I say for truth, or yeah, don't rely on anything I say, but I hope to at least get some basic ideas across. So the idea about functional analysis is you treat functions as vectors. So because vector space is a set of elements that has addition and multiplication and it satisfies certain properties like commutativity, one can think of functions as a vector space. We define addition of two functions pointwise and same as multiplication. Then for a vector space, you think of the notion of a basis. So what is, because you have this addition structure on the function on the vector space, you want to find the concept of a basis is there a set of vectors that can be combined in a linear combination to span the entire space. So formally, a basis is a linear independent set of vectors that spans the entire space. So there's two concepts here. One is linearly independent, one is span. So for finite dimensional, this would be a finite set. You only need a finite set, and the linear independence is encoded in this, meaning that if you have this sum of basis vectors that is the zero vector, then it implies that the only way to solve this is that all of ai is 0. Basically all the coefficients are 0. So that's what linear independence is. And for span, it means that any vector in the vector space can be expressed as a finite linear combination of basis vectors. So it's a finite linear combination. So however, this is for the case of finite dimensional basis. We want our vector space of functions is infinite dimensional. So we need a notion of infinite dimensional basis. So there's two bases. One is the Hamel basis and one is the Schauder basis. I'll go through the Hamel basis first. So it can be proved it's related to the axiom of choice, or so I think it's a Zorn's lemma axiom of choice, that every vector space has a Hamel basis. But so that is there's a proof involving that. But what is a Hamel basis? A Hamel basis is a set B which is possibly infinite, which is number one, linearly independent. But if we want to say the same thing as the previous slide, in the sense that we add up infinitely many vectors, that's not the definition that we want, because the case for linear independence of a infinite set of vectors is that every finite subset is linearly independent. So if you have infinite number of vectors in B, and you want to say that B is linearly independent, in the definition of Hamel basis, you want to say that a finite subset of this infinite subset is linearly independent. Every finite subset, I mean, yeah. So as you can check that every finite subset is linearly independent, then you can say that the infinite set of vectors B is linearly independent. So this finite set is an important term here. Then for the span, you're going to say that any vector V in the vector space can be expressed as a finite linear combination of basis vectors, of finite linear combination V1 to Vm, where V1 to Vm is a finite subset of the infinite set B. So then we want that the span of B is the vector space V. So now that's for Hubert basis. If the Hubert basis is the more powerful notion of Schauder basis, it's sort of a Schauder basis is you'll see later that the Schauder basis is actually a bit in a sense not very rigorously but in a sense smaller than the Hubert basis because we relax the conditions for Schauder basis. So the Schauder basis, the upshot is that instead of taking finite sums, you can take infinite sums. So the Schauder basis defined as a sequence of elements of a sequence of vectors in V such that every element V there exists a unique sequence of scalars that satisfies this condition. So you can see that previously we took a finite linear combination, but now we're taking an infinite linear combination. So when you take infinite sums, you have more power in a sense because when you take infinite sums, you don't have to hit it exactly. You just need to converge to it. So in that sense, a Schauder basis is smaller than a Hubert basis. But if we want to take the infinite sum, it comes at a consequence, meaning that if we want to have a more powerful notion of a basis, you need to take an infinite sum which relies on the concept of convergence, and convergence relies on topology. So what this means is we need a topological structure on V. We need open sets on V. So so we see the additional structure can come from a norm, and this is called a norm-induced topology, meaning that for a norm, when you have a norm, you measure you can take in the norm takes a vector to the field, most likely the real numbers or the complex numbers. Sorry, most likely the real numbers. So the norm sort of measures the length of a vector. So if you have a norm, then it naturally induces a metric topology because yeah, the metric, so the norm induces a metric and the metric induces a topology. So that's what a norm-induced topology is. So then what do we mean when we say V is the infinite linear combination like this? We mean that we take the finite linear combination and then we take the limit as n goes to infinity, as the n over here goes to infinity. And because this if we have a norm structure on it, if this term inside converges, then we can say that this converges to V, and that's what the equal signs over here means. So now a Schauder basis, the span of a Schauder basis is dense in V, meaning that if you take if I'm not wrong, if you take every possible linear combination of finite linear combination of S as well as the limit points of where the finite combinations can go to, in other sense this limit, then the closure of the span of S is equals to V. So that's what density means, and topological closure, I covered it in another video on topology. So now that we have a notion of Schauder basis, let's talk about Hubert spaces. So previously we mentioned that there's a norm vector space, right? You have a vector space and you give it a structure of a norm. Well, Banach spaces are defined to be complete normed vector spaces. So completeness means that every Cauchy sequence converges. Is it? Yeah, I think completeness means that every Cauchy sequence converges. So there's additional condition on the norm in this case, or the entire structure in this case. So as mentioned previously, a norm induces a metric which allows us to define the open ball topology, the metric topology. And then a Hubert space is defined to be a vector space, a topological vector space that has an inner product. So once you have an inner product takes two vectors to something like the real numbers or the complex numbers, the field that you consider. So the inner product is a way of pairing two vectors, and an inner product induces a norm and hence induces a topology, a normed topology. So a Hubert space is a vector space that has an inner product, and when you have the inner product, you naturally induce a topology. So it becomes a topological vector space. So a Hubert space is also a Banach space with the definition of the norm here. So completeness is the condition that every Cauchy sequence in V converges to element in V. Yeah, as I mentioned previously. So example of completeness is R is complete because every sequence you can think of in R converges to an element in R, whereas Q might not be complete because if you have the Cauchy example, if you have Cauchy sequence this, you check that it's Cauchy, you can check the conditions that it's Cauchy, but this converges to square root 2, and square root 2 is not in the set of rational numbers, so Q is not complete. So completeness is in a sense a notion of whether the space has holes. Yeah. So Hubert spaces are Banach spaces with additional structure, yes, where the inner product naturally leads to the norm. So then let's define something called a bounded operator. So a bounded operator between a normed vector space and a Banach space is bounded if the supremum of this quantity here exists, or rather it is not infinity, meaning it is finite. So what is this thing over here? So to understand what this is over here, we have a linear operator L. To check whether it is bounded, we take every single vector in F, and then we apply L to F, and then we take the norm. LF returns a vector in the Banach space W, right? So we take the norm of this LF vector, and this norm will exist is the W norm. We take this W norm and we divide it by the V norm of F. So in a sense, this is sort of taking the unit vectors in L, in a sense. So this just makes sure that essentially we want to make sure that the operator is small enough when applied to a vector. It does not indefinitely increase a certain vector to be very huge. For example, the derivative operator is unbounded because you can have a function that is bounded. Sorry, you can have a function that is not infinite, but then once you take the derivative, perhaps at one point the gradient is very steep. So in that sense, the derivative operator is not bounded because it can take small vectors and spit out large vectors. That's very unrigorous, but yeah. So if L is bounded, then the norm of L is defined to be this supremum. So you can see if it's bounded, then it's finite. Then L is a finite. The norm of L is a finite number. So the norm over here exists on it's not the same space as W or V. The norm here is the norm in the set of bounded operators from V to W. Well, turns out with this definition of a norm, remember previously we said that when you have a vector space and you have a norm, you can check that if you check that it's complete in the sense of a norm topology, then the vector space with the norm is a Banach space, and it can be proven. You need to show a couple of things. Namely, it can be proven that the set of all bounded operators from V to W equipped with this operator norm is a Banach space. So what this means is we need to check a few things. We need to check linearity. We need to check scalar multiplication. Then we need to check that the norm is indeed a well-defined norm, meaning it satisfies three properties, the properties of a norm. Then we need to check, in order for it to be a Banach space, we need to check that this norm is, with respect to this norm, every Cauchy sequence is convergent, meaning it's complete. So there are a few things to check over here that I definitely did not check, but it can be shown that it is a Banach space. So that's interesting. So then we have a Hubert space. So right now we have the notion of the space of set of bounded operators, right? So the dual space of a norm space is defined to be this, where W, remember that W only needs W is a Banach space, right? Complex numbers is the sub in W equals to C, then this is, and you can show that it's Banach. So that's the definition of the dual space of a normed space. And so previously we said that the set of bounded operators is a Banach space. So if given a Hubert space, if you have this the set of bounded operators from Hubert space to itself is a Banach space, no surprise. However, what is surprising is that the dual of the Hubert space, which is the set of bounded operators from the Hubert space to the complex numbers, is a Hubert space itself, meaning that we have some additional structure when we go from Banach space to Hubert space. And what is this additional structure? The additional structure is a inner product, and this is defined, the inner product is defined as such, where the norm is the norm on the where the norm here is the operator norm, the operator norm of the set of bounded operators from the Hubert space to the complex numbers. So this is called a polarization identity. So the dual of a Hubert space is a Hubert space, whereas a dual of a norm space is only a Banach space. So then there's additional structure, additional conditions we can put on the Hubert space, namely separability. So definition, a separable Hubert space is a Hubert space that has a countable orthonormal Schauder basis. So remember previously we talked about Schauder basis, about taking infinite linear combinations. So the theorem, there's essentially only one separable Hubert space up to unitary isomorphism. So it's isomorphic to the set of square summable sequences defined as such, where the map is given by this, and this makes sense because if you have a countable orthonormal Schauder basis, you can project it onto each Schauder basis and you get a sequence of coefficients. So yeah, but you need to prove it. So what is a unitary map? A unitary map is a bijective linear bounded map. So essentially there's a condition of being bounded over here. It's a bounded map that respects the structure of a Hubert space. So the additional condition over here is bounded. So then let's talk about Lebesgue spaces. So if this requires prerequisite notion of measure spaces. So you need to understand what a measurable space first is. Then you need to understand what a measure space is, which is a measurable space equipped with a measure, and the measure must satisfy certain properties as well. And then after that, you can define measurable functions to be the map between measurable space or some, but there's a definition of measurable functions that satisfies measurable functions that satisfies this norm defined to be this, where the integral over here is the Lebesgue integral. They form a vector space. However, this is not quite a well-defined norm, I think. It is not a well-defined norm. It's called a semi-norm. It's not a well-defined norm because it does not satisfy the property that norm of a vector equals to 0 implies that a vector is 0. However, if we define the equivalence relation that two measurable functions are defined to be equivalent if they are equals almost everywhere, where almost everywhere is basically they are equal everywhere except for a set A which has measure 0. Then if we take this equivalence relation and we take this vector space and we quotient out this equivalence relation, basically we take the vector space of measurable functions that are bounded, sorry, not bounded, that have there is a finite P norm, and we quotient out all the almost everywhere, almost equal almost everywhere functions, then we get a Banach space. So in the special case of P equals to 2, which we get a Hubert space where the inner product is defined as such. And this is called the square integrable functions. And yeah, so this is, at this point I have not understood the proof by myself, but so if we think about the set of periodic functions as L2 of a certain range of a certain domain, because it's periodic, then we get there's a certain Fourier series of you can show that the Fourier series converges to L2, converges to U in L2. So for it to converge, you must have the notion of topology, and this means that, and then there's a, from Fourier's theorem, you have a set which is an orthonormal basis of this vector space. So the vector space is the vector space of periodic functions, as well as some other conditions like square integrable. Then you have a set over here that forms an orthonormal basis, and you can show that it's complete also, meaning that any I think, okay, complete over here does not mean the Cauchy sequence is convergent thing. I think complete over here means that you can form any vector with the as a infinite linear combination. Yeah, so it's the complete in the sense of span, in the span sense. So you can show that this set spans the entire vector space of functions. So lastly, there's a theorem called the Spectral Theorem, where basically you're saying if you have an operator with certain conditions, then an orthonormal basis, that there is an orthonormal basis of this vector space consisting of eigenvectors of this operator. So I have not understood and read the proof of the Spectral Theorem, but yeah, but this is where I'm going to stop, because I think I've bitten off more than I can chew. So I hope that I have at least shown my enthusiasm for this subject, and I was a bit ambitious at the start, so unfortunately I will not be able to continue learning all of functional analysis, because yeah, I don't have the prerequisites needed or the time required to spend on them. So that is the end of the video. Yeah, have a nice day.